So let's do reductions. Let's start out with reducing agents. Does anyone remember any of the reducing agents? Yeah, okay, so we're gonna split that up into strong and weak. So LiAlH4, is that strong or is that weak? Strong. And what's the other one? NABH4. Cool, the way I remember this is really stupid, but bear with me. Al is BH. A comes before B in the alphabet, therefore A is stronger than B. Oh, welcome. Okay, that's it. So, yeah, lithium aluminum hydride and sodium borohydride. Okay, so this is really, really important. The reducing agents are LiAlH4 and NABH4. But the reducing species, which is the actual thing doing the reduction, is what? What do you guys think? H. So H minus. So if he asks you for a reducing agent, it's those two. If he asks you for a species or the thing that's actually doing, that's H minus. So we're going to kind of do what we did for oxidation, but backwards. But, all right, so this is another one of those things that isn't really a scientific thing, like you find it in your text, but I made it up, and it's helpful. So we're going to use that. So we're going to have group 1 and group 2 reductions. So group 1 has aldehydes and ketones. So aldehydes and ketones, these are more reactive. And they can use either so aldehydes and ketones are more reactive than group 2. We'll talk about group 2 in a second. And they can use either reagent because the more reactive they are, the less strong of a reagent required. So let's see what that actually looks like. I'm going to zoom in. I promise I'll zoom out at the end. So I said we could use either reagent. And what is the thing that's actually doing the reducing? H minus. So how this is going to go is the H minus is going to attack the carbonyl carbon, and it's going to bring those electrons up to the oxygen. So we get bam, bam. What charge do we get on the oxygen? -1, because it has an extra pair of electrons now. And bam. So what do we do at this point? What do you guys think? Yes, we are going to protonate using the water. So I mean, why do you think it would be more positive? Yes, but okay, so when we have carbonyl, right, you can do resonance and you get this, right? So the delta plus here is more positive than just the sp center. have as strong of a delta plot. Okay, that's fair. All right, so we're going to protonate. I'm pretty sure you guys said that. And now we get an alcohol. What kind of alcohol is this? Primary, because there is one carbon group attached. So we can say in summary that an aldehyde plus either equals a primary Now we're going to do the same kind of thing for a ketone. And we know that it's the same deal. It's still part of group 1, so you can use either reagent. And the reducing species is still H minus. So once again, we're going to attack the carbonyl carbons. We're going to bring those electrons up. Get an O minus again. So what do you think we could possibly do? What do you think we could possibly do at this point? Protonate. Cool. Okay. So this O is going to steal a hydrogen, give those electrons back to the oxygen, and now we get. So what kind of alcohol did we make now? A secondary, because now we have 2 carbons here. So we can say in summary that a ketone plus either equals a secondary alcohol. I'll give you a second. Yes. I can. I'll zoom in and then I'll move it over. Just make this bigger. I don't know why. I could do this, but then it like doesn't show the whole. Wait. All right. So, any questions about this? Questions, comments? If not, I'll give you a couple more. 2. So, just purely based on what I wrote for group 1, do you have any idea what group 2 could be? Esters and carboxylic acids. Awesome. So, and these are going to be less reactive. So if it's less reactive, which reagent do we have to use? Weaker one or the stronger one? The stronger one. So it needs. Which one is stronger? Yes. I had to zoom in because I couldn't that with that. Less reactive and need to use LiAlH4. So we know that carboxylic acids and esters are less reactive than aldehydes and ketones. Does anyone have any idea? If not, remember those 2 things that I said? Basically, if you don't know the answer, you can use those 2. resonance and induction. Cool. So very quickly, let's compare aldehyde, ketone, carboxylic acid. So resonance for this one, not as much, but we're going to talk about sterics. So when we say more reactive, we're talking about a reaction where something attacks the carbonyl carbon. So we want the least steric hindrance. So an aldehyde just has a hydrogen and a methyl. Ketone just has two methyls or whatever carbon. And then we have these huge oxygen groups. So aldehydes and ketones have less steric hindrance, which makes it more reactive. Because an electrophile, aka nucleophile, aka something that's attacking it, can get in there more deeply. And then inductive effects. From Orgo 1. You guys remember vaguely files, right? What those are? Okay. Electron rich, yes, there are things doing the attacking. So the electrophile is the thing that's getting attacked, right? And so we'll talk about this more later, so I won't spend too much time on it. But basically, we want a more positive charge because that's more likely to get attacked. So here, I already told you that we have a delta plus and a delta minus. And this is actually where NMR can kind of come in handy, right? Because when we talked about NMR, we talked about inductive effects and donating groups. What did we say about that? Any ideas at all? Okay. Yeah, something about shielded and deshielded. So this group, the carbon group, is going to inductively donate a little bit of electron density. This one has double the donating group. This one has one donating group, and then it has the one resonance donating group. And same here, it has the resonance donating group. So the one with the least amount of donating groups is going to be the most delta plus, which means this is more delta plus than this one, and this is more delta plus than either of these two. And more delta plus. So this is how I kind of want you guys to think about it. Any questions? So let's just get rid of this. I am going to erase it, so does anyone want me to not erase it? This room is like simultaneously hot and cold. It's so much easier than wiping off a wipe. All right, so group 2, let's see how those reactions work. All right, which reagent do we have to use again? The strong reagent, LiAlH4, but what's actually doing the reducing? H minus, cool. So, what do you think is going to happen in the first step? You're like very lowly. The H is going to attack. Going to attack the carbonyl carbon, and these electrons again are going to go up. So we're going to get at the 8. All right, so at this point, what can we do? Ah, it was a trick question. Not really a trick question, but you would think, oh yeah, that's what we've been doing, and she made that voice, whatever. But this time, we actually have an OH. And despite what they told you in Orgo 1, OH is not an alpha leaving group. It's going to count as a leaving group. So instead of just protonating, we're going to bring these electrons down to reform the double bond. And we're going to kick off the leaving. And so you might be thinking, okay, so what's a leaving group then? So we're going to consider in this class anything that's like a heteroatom. So a carbon bonded to a heteroatom, that bond can break. Like NH, SH, OH, all that kind of stuff. Talk about that more. For now, you just have to worry about carboxylic acids and. All right, so what functional group did we make now? An aldehyde, yes. Okay, so are we done? No, because I said it in a weird voice, right? What can we do now? I mean, okay, good. Why would we protonate? What do you guys think? We do have a water, cool, but do we have a negative charge? Do we really? We could add another H minus, exactly. So we assume that we have more H minus, right? In solution, we're going to say that there's always enough. And we're going to come in here and bam, bam. So just like we did in group 1, it's just going to attack one more time and pick up those electrons. And we get minus. So now what do we want to do? Protonate. Whoever said it before is like, I'm not saying that. I'm so sorry. Okay. So we have H2O, protonate, and we get something we've never ever seen before, primary alcohol. Ta-da. I'll zoom out. So we can say that a carboxylic acid plus LiAl4 equals a primary. Okay. So any questions about how / why I did any? So you mean like the last step? Oh, okay. So the reason we did that is because LiAlH4 is super, and we're assuming that we have a lot of it in. And so if we start reducing this and we make an aldehyde, we saw that an aldehyde get reduced and form a primary alcohol, right? So since we went to form an aldehyde, we had a carbonyl again, so it had to get reduced. So since we still have double bonds, we're going to reduce. Exactly. And the best part of this is that this reaction is pretty much exactly the same for ester. All you do is change that H to a carbon group. So we'll say ester plus LiAlH4 gives you a primary alcohol. Yeah, pretty much. So in this class, there won't be a lot of like mechanism questions. There probably won't be questions. You just really have to know the starting material and the final product, which is why I've been doing it. You know, carboxylic acid plus Al and blah gives you a primary alcohol. Yes. On the what? Yeah. Unfortunately. Okay. Let me. I don't know if Dr. West gave this to you yet, but I'm gonna kind of give you a list of the concepts that you need to know for this.
Wow, we have to do it like 3 days before. He gets to do it the day of.
Yeah, for real. So, clean that up for you. And I will give you the spiel one more time. I don't make your exams. I don't see your exams before you take them. This is the list Dr. West gave me. So you're not allowed to hate me if this doesn't reflect your exam. Yeah, I tell that every single semester. If for some, okay. Someone yelled at me once. They were like, "Why'd you make it so hard?" I was like, I didn't make the exam. And it wasn't even like, I don't know. I was like, okay, bro. Anyways, does anyone still need us up? And I know he words things kind of weird. So if you have any questions about that, let me know. So now we're going to segue this into something called the Grignard reaction. Like, what is that? And also the way it's spelled is even worse. The Grignard. I literally used to spell it Grignard, and nobody corrected me, so it's fine. Anyways, so the Grignard reaction is a type of reduction, but instead of using an H, we're going to use a carbon group. So this is why that's kind of a good step. So the first thing we're going to talk about is how to make a Grignard. And so you might be asking, what the heck is a Grignard reagent? Well, we're going to turn this into kind of like a soap opera moment, and that'll probably help you remember it, I hope. So, we have this lovely couple, right? Carbon and bromine are so happy together. They've been bonded for a long time. Cool. It's an alkyl halide. And then they're just going about their happy, merry way. And then magnesium is a hoe, right? Magnesium is a home wrecker. Magnesium comes in here and he's like, I want me some of that bromine. So it's just going to come right in. It's going to break them right up and slide right in the middle of those two. That's unfortunate, right? And for a long time, carbon has no idea that magnesium is in between him and bromine. So sad. So this is carbon's perspective. Carbon is like, what the heck? Like, I didn't know you were just in the middle here being a home wrecker. But we as the audience know. So we're gonna see that magnesium stole bromine completely. So carbon is now all alone. And he's so alone, he's negative. So sad. And then magnesium is like, haha, pull your mans, and I'm not even sorry. Very positive. He has the bromine. So to the outside world, it's just like, okay, it looks like they're all bonded together. They're still happy. Magnesium's just hanging out. But we know that in reality, they had a terrible breakup. Carbon is super negative, and now magnesium bromine is chilling it. All right. Now, you know what happens after you break up and you've had your like heart broken, right? You want someone else. You want to be in another relationship. And carbon's not picky, right? So carbon is going to be a very strong nucleophile and a very strong base. So, right quick, let's take an intermission. What does this mean? So, a nucleophile is something that has extra electrons, right? We want to have more electrons. So, it uses its electrons to attack bond. So what this means is it's attacking another molecule and it's bonding to it. So it's adding itself to another molecule. Versus a base is using its electrons to steal or just so that's the difference between a nucleophile and a base. And carbon does not care. Carbon's like, sure, I want to be, a nucleophile and get into like a nice stable relationship. But also, if there's like a hydrogen out there that's really desperate and acidic, I'm just gonna snatch it right up. And so this sad, lonely creature is what we call the Grignard. So that wraps up season 1. Thank you. Thank you. I should become a screenwriter. So now that we made the Grignard reagent, we're going to start season 2, a completely different reaction. Now we're actually doing the Grignard reaction. And we're going to use any carbonyl. So I'm going to start with ketone. And we're going to react it with the Grignard reagent. And so when he gives you the Grignard reagent, he's going to write it like this. Right? But we know that it actually looks like this. Right? Because they're not really in the picture. And always count your carbons because I've seen so many people just absolutely wrecked because they didn't count their carbons. So 1, 2, 3. And whenever you have a Grignard reagent or a Grignard reaction, first thing you're going to look out for is an acidic hydrogen, right? Because it can just act like a base and steal a hydrogen. So what do we count as acidic hydrogens? Well, kind of. So these acidic hydrogens are like actually very specific. So we're going to count triple bonds, carboxylic acids, and coming off of a heteroatom. So OH. So that's what counts as an acidic hydrogen for the Grignard. Do we have any of those? Do we have any acidic hydrogens on our ketone? No, we don't. So, since there's no easy peasy hydrogens for us to grab, the Grignard is going to go ahead. That's the dumb way to do it. Going to attack the carbonyl carbon and kick those electrons up. Very similar to what happened in the reduction reaction. But now, instead of an H minus, we have a C minus. Not what you want to get. Okay, thank you so much for the pity. So now, I know I didn't draw it in blue, but I'm going to make it blue so you can kind of 1, 2, 3 carbons. Now, do we have any way to like reform the double bond, take off any group? Okay. All right, but what would we kick off? We can't do that. Did you have 3 carbons? So it's going to be 1, 2, 3. But thank you for asking because I'm sure there were other people who were also questioning. Okay, so we're not able to kick anything off because in order to kick off a leaving group, you have to reform a double bond. But the only thing that could possibly act as a leaving group is the O. So we don't have anything to kick off. So we have to use the water and protonate it. Any room whatsoever. Okay, I got a lot of blank stares. Oh, I did have a lot of room. Any questions on this? Why we didn't reform the double bond? Why it was hacked? Anything I said? Another moment. Ready. Okay, so what if we did have a leaving group? So let's try what is this function? Ester, yes. So let's say we have an ester, and let's use, just for funsies, So this is again our Grignard reagent. So what is the first step going to be? Yes, so we're going to attack the carbonyl carbon. Bam, pick up these electrons, bam. And we get minus, and we get 1, 2, now what? What? Yes. It does because we had to add this, we have to add bond to that first carbon. So it looks like there's an extra carbon, but that's just because we had to like actually make that. Yes. 1, 2, 3, 4. Let me just. Yeah, so whatever they give you, that's what you have to use. So in this example, we had a 3 carbon chain. In this example, we have a 4 carbon chain. And you can't rearrange the Grignard. So whatever they give you, that's what you do. Alrighty. What do we think could happen? You could protonate, or if we think about a reduction reaction with an ester, what else could we do? Yes, we can. We're not necessarily going to make a primary, but like I told you guys, a carbon heteroatom bond can break. So this can be a leaving group. So we're going to bring these electrons down and we're going to kick off the leaving group. So we get, that is a gigantic oxygen, but whatever. 2, 4. So what now? Are we done? No, why not? Yeah, so you have to make it into an alcohol. So just like a reduction reaction, since we made another carbonyl, we're going to attack one more time. We're going to assume we have enough Grignard reagent to attack again. So as long as we have a carbonyl, we're going to attack again. And I'm going to make it a different color just so. And it's going to attack the carbonyl carbon again, pick up those electrons again. So we're going to get a big messy thing. Bam. Bam. No, it's ugly. Really resisting the urge to fix it. Okay, so now what can we do? We can protonate. Bam. Bam. So it's exactly the same thing. I just made it. Sound. Questions, comments, concerns? I see a lot of people avoiding eye contact. There. So what are we thinking? No. Okay, the questions are actually going to be a lot more straightforward than right? Because as long as you know what the starting material is, what the Grignard reagent is, all you have to think is no leaving group, you add the Grignard one time. Have one leaving group, add the Grignard two times. So if you have this final answer is just going to be an alcohol plus two of these. If you have an aldehyde, it'll be an alcohol plus one of these. Yes, so no. One leaving group equals two. And then theoretically, if you had two leaving groups, you would add three, but that's not. Okay, cool. Exactly. So when do we protonate versus when do we? We're going to reform the double bond and protonate anytime we. Yes. So we are going to reform anytime we have a leaving group. Form the double bond anytime we have a leaving group. We are going to protonate and we have nothing else. So it is 11:50. Last questions, comments, concerns about this, about the exam, about the class. Your stuff. Yes. Just know it's going to be exactly the same reaction. We don't have to finish chapter 11. Hopefully, we'll be able to do everything for the exam. If not, yes. So yeah, we have the exact. Yep. So if we ever have like a group like this, carboxylic acid, it'll be no reaction. Or if we have that'll be no reaction. Or if we have a triple bond. Yes. Yes, I'm sorry. So the whole point of the whole add a carbon group. So okay. Stop recording. Yes. Question?